Here is a combined summary of the 4 pages. The paper explores the K-center problem in a distributed setting, where the underlying metric is the graph's shortest path metric in 3 canonical distributed models: local, CONGEST, and CLIQUE. The K-center problem seeks to locate a small set of points in space that minimize the maximal distance from them to any other point. The authors present upper and lower bounds for the K-center problem in different distributed models, with the metric being the shortest path metric and the graphs being unweighted unless otherwise specified. In the local model, a 2k plus e approximate algorithm finds a solution to the K-center problem in O, k, e rounds. But reducing the approximation ratio to below k1 requires omega n time. In the CONGEST model, a 2 approximation algorithm runs in O, kd rounds. But improving the approximation ratio to below 4/3 requires omega n k rounds. In the CLIQUE model, the authors consider the congested CLIQUE model, where the communication graph is a CLIQUE, and the input graph is a subgraph of it on the same set of nodes. The authors also study the K-center problem in the context of distributed graph algorithms, specifically in the CONGEST and CLIQUE models. A 2 approximate solution for the K-center problem can be found deterministically in O, n⁻⁻⁻⁻, time for weighted graphs, and O, n⁻0.158, time for unweighted graphs. Furthermore, if the exponent of the centralized matrix multiplication problem, omega, is discovered to be 2, the time for distributed matrix multiplication algorithms for 2 approximation of K-center will also be improved. The paper discusses the computational models for studying distributed graph algorithms, including the local, CONGEST, and CLIQUE models, and surveys related work in traditional distributed computing models and works on the related problem of metric facility location in distributed settings. Additionally, the paper establishes a lower bound of omega L for the two-party set disjointness problem, which holds for deterministic and randomized algorithms alike. The paper explores the K-center problem in distributed models, particularly focusing on the local model and its relationship with other computational models such as the CLIQUE model, MPC, and K-machine model. It introduces a simple and fast deterministic algorithm that achieves a 2 plus epsilon k approximation for the K-center problem in the local model. This algorithm leverages the power of local computation in the local model to find an optimal solution or a 2 approximation in a greedy manner, maintaining the required approximation ratio and reducing local computation time. Additionally, the paper provides a lower bound for the K-center problem in the local model, stating that any Tround algorithm cannot achieve an approximation ratio better than kk squared plus k, beta k1, 2t plus 1, n plus k, where n is the size of the graph and beta is greater than or equal to 1. This lower bound is significant when k is a constant, implying that achieving an approximation ratio better than k1 requires linear time. The proof of this lower bound involves constructing a communication graph that is a cycle, and analyzing the performance of an algorithm in the local model against this graph. By creating a new cycle by concatenating segments around chosen centers and considering leftover nodes, the paper demonstrates that executing the same algorithm on the new cycle leads to a contradiction if the approximation ratio is better than the stated lower bound. Furthermore, the authors present a proof for Theorem 1, which states that any algorithm that finds an approximate, bicriteria solution for the K-center problem has an approximation ratio of at least kk squared plus k, beta k1, 2t plus 1, n plus k. The proof involves constructing a new cycle C, by rearranging the nodes of a given cycle C, such that the solution found by the algorithm for C has a bad approximation ratio. The cycle C is constructed by concatenating segments C plus 1, C plus 2, Sk followed by S1, S2, C, and finally all the remaining nodes of C, in a clockwise order. The authors show that the distance between C and C plus 1 is more than 2t, and hence, the neighborhood of length t for the nodes C and C plus 1 is disjoint. This implies that each node C receives the same information in both C and C, and therefore, each node C makes the same decisions. The authors then discuss the approximation ratio, showing that there are at most, k, 2t plus 1, nodes in C plus 2, C plus 3, Sk, S1, S2, C1, and hence,
The distance from C plus 1 to C in the anti-clockwise order is at least n, k, 1, 2t plus 1, plus 1. Lastly, the authors present a two-approximation algorithm for the k-center clustering problem in the CONGEST model, which achieves an approximation ratio of 2 in O, kd, rounds, where d is the diameter of the underlying graph. The algorithm, algorithm 2, consists of finding the node vmin with minimum id, and then performing k1 iterations of BFS from all nodes in S, where S is initially set to vmin. In each iteration, each node chooses to join the first BFS tree that reaches it, and the furthest node from S is added to S. The algorithm terminates when S contains k nodes, which are marked as centers. The authors explain each step of the algorithm in detail, including how to find vmin in O, D, rounds and how to disseminate the depth of the BFS tree along the tree. The authors present a deterministic two-approximation algorithm for the k-center problem in the CONGEST model, requiring O, kd, communication rounds, building upon the known greedy approach by Gonzalez. A lower bound on communication rounds for any algorithm with an approximation ratio better than 4/3 is established, using a graph construction similar to that of Abood et al. The graph Gx, Y consists of nodes in sets A, B, Fa, Ta, fluorine monoboride, and Tb, with specific properties stated in Claim 1, crucial for the lower bound proof. These properties establish that for every node U not in A, the eccentricity ECC, U, is at least 4, and for every node I in A and any node U not in B or CB, the distance D, I, U, is at most 3. The authors prove that the distance between a node I in set A and a node Bj in set B in the graph Gx, Y is at most 3, and defined two strings x and y as disjoint if there is no index I such that x, I, equals y, I, equals 1. Lemma 3 shows that op1, gx, y, equals 4 if and only if x and y are disjoint. Theorem 3 states that any CONGEST algorithm that returns an alpha approximation for the one-center problem with alpha less than 4/3 must take omega n log 2n rounds to complete. The authors extend the lower bound to the k-center problem by considering k copies of the graph Gx, y, denoted as gkx, y, and prove that any CONGEST algorithm that returns an alpha approximation for the k-center problem with alpha less than 4/3 must take omega n k2 log 2n rounds to complete. The authors present a two-approximation algorithm for the k-center clustering problem in the CLIQUE model, applicable to both weighted and unweighted distances. This algorithm consists of two phases: computing all pairs' shortest distances or approximating them, and greedily finding the centers in k rounds. In each round, the furthest node from the current set of centers is added, ensuring that all nodes are within a certain distance from the centers. Lemma 4 proves that if an alpha approximation of all pairs' shortest paths is computed in the first phase, the algorithm returns a 2 alpha approximate solution for the k-center problem. The time complexity of the algorithm depends on the approximation ratio desired. Theorem 5 states that there exists a deterministic clique algorithm for the k-center problem which gives a 2 approximation in O, n caret 1/3 plus k, rounds on weighted graphs and O, n caret 0.158 plus k, rounds on unweighted graphs. For every constant 0 less than e less than 1, there exist deterministic algorithms that give a 2 plus e approximation in O, n caret 0.158 plus k, rounds on unweighted graphs, a 4 plus e approximation in O, log caret 4 log n plus k, rounds on unweighted graphs, and a 6 plus e approximation in O, log squared n plus k, rounds on weighted graphs. The authors also provide an extensive list of references related to distributed algorithms for facility location problems, including metric facility location, uncapacitated facility location, k-center, and clustering. These references cover various models, such as the congested CLIQUE, CONGEST model, and distributed computing models, and propose fast and efficient algorithms, including distributed approximation algorithms, online algorithms, and primordial approaches. The cited references demonstrate a thorough understanding of the existing literature on distributed algorithms for facility location problems.